Thank you. I'd like to introduce Liang Yu, who will tell us about some consequences of Turing determinacy and variation of Turing determinacy.
Okay, thanks. Okay, I gave the almost identical talk in CTA seminar. So Stephen Lamb was there, and he told us, okay, TD means Turing determinants, and sTD means strongly Turing determinants. But Stephen Lamb told me sTD has a different meaning in English. So apparently it's very often. So we decided to keep it. Okay, let's review some set theory notations. Okay, let AD be the axiom of determinants. So I guess you all know what is AD, and because Linda has already mentioned it, Borel determinants, so I guess everybody knows. And Turing determinants says for every set of Turing degrees, either A or the complement of A contains an upcomb. Upcomb means okay, an upcomb is a subset of Turing degrees, such that like this X and this Y Turing about X equal to U is a upcomb. And the strongly determinant says every set of reals, if the range is Turing degrees cofinally, then A has a pointed subset. So what does it mean? Range is Turing degrees cofinally. It means for any X like this Y in AA, Y Turing greater equal to X, A has a pointed subset. A pointed subset is a perfect set T or P, subset A, such that for any X in P and X Turing computes the presentation of this perfect subset. So it's called a pointed subset. So clearly STD implies TD. And the important consequence of AD is over ZF, AD implies STD, implies TD. This was proved by Tony Martin to get a contradiction from AD, but clearly we don't know whether it's a contradiction. So this is the history, okay? And TD, YTT is important because it's very natural. It looks much natural than AD, and it's very neat. And actually, in set theory, when people use AD, most of the times they use TD, especially for some in the model theory, and they use TD as axiom to get some consequence. And so yeah, and yeah, and let's review some axiom choice. Okay, given non-empty set A, let CCA be the countable choice for subsets of it. It says for any countable sequence of AN, such that for any AN subset of A and non-empty, then there is a function from omega to A, such that for any N, Fn pick up an element from AN. And this DC, dependent choice for subset of A, is said for any binary relation R over A. If for any X, like this Y in A, RXY, then there's a countable sequence Xn, such that for any N, R, Xn plus 1. Yeah, this is a dependent choice. So if for all A, CCA, and we use CC to denote for any A, CCA. We use DC to denote for any A, DCA. AD implies the negation of AC. It has a contradiction with the AC. But AD implies a fragment of AC. He proved CF plus AD implies CCR, countable choice for set of reals. And calculus, he proved actually in V, if you assume CF plus EV equal to LR plus AD, then DC is true. So this is the relation between AD and DC. And but the long-standing question in that series is whether CF plus AD imply TCR. We don't know. That is a long-standing question in that series. And we need a piece of Excel choice like CCR. CCR is the weakest base we need from Excel choices. Fortunately, we don't need to assume CCR because Peng, Yinghe, and I proved that CF plus TD implies CCR. So we just need to assume CF plus TD, and we don't need additional assumption for CCR. Yeah. Here's some questions related to set theory and recursion theory. So we don't know whether CF plus TD implies DCR. And we don't know whether calculus result holds if we replace AD with TD. So we don't know these questions. Yeah, these are open. Okay, let's look at weakly dependent choice. Before that, let me give some remarks about how to apply recursion theory to set theory. Okay, mostly we focus on the module theory or category theory or some other property for sets of reals, and so with CCR plus CF. So let's look at the sets of reals. Okay, QSA subset R, and A is null. How to characterize a null set? We can prove by CCR if A is null, if and only if like this X for all Y in A implies Y is not X random. Yeah, so this random has lots of different meanings. You can say Martinov random or Schnorr random or delta 1 random, whatever sense. So this build a connection between analysis and recursion theory. So but this fact, of course, this fact is trivial because by CCR, this is trivial. This is trivial fact, and you cannot expect too many things can be proved using this fact because it's too trivial. But there is a very special things in recursion theory. It's a very unique notion called lowness properties. It's very unique, and you cannot find any similar notation in analysis. And you can use lowness properties plus these randomness notions, and together put them together and prove some result in analysis. So we will see how to apply this argument. So now let's look at the weak version of dependent choice. So let's WTCR means binary relation R. Binary relation over reals. So for any X, Rx, this means for the reals Y has a relation with the X has a positive in the module. Because we don't assume whether every set reals is measurable. We just assume it has some positive in the module. Then there's a sequence Xn such that for any n Rn Xn plus 1. So we want to use TD to prove the weak version of the dependent choice. And to prove this, we just need to assume this set for any x, Rx has margin 1. Has margin 1. Or conar. Just because take the Turing closure, you can assume this is Turing closed on the this is closed on the Turing equivalence relations. So you can that means if it has positive in the margin, then that means the master have it's conar or it has margin 1. So now let's look at how to apply randomness to prove this result. So we prove ZF plus TD implies WDCR. Now the idea is like this. So we use Schnorr randomness because we don't use the standard notion like a Martin-Loff randomness. The point is the lowness for Martin-Loff randomness is bad. There are only countable many reals low for Martin-Loff random, but there are uncountable many reals low for Schnorr random, and it has a perfect subset. So that's a very good thing, and so we let this advantage makes us can use lowness. Okay, let's look at the proof now. For any y, so y jump compute the Schnorr random relative to y. Y jump compute the Schnorr random relative to. Now let's find real x, two real about x, two real about y. Sorry, two real about y, and the low for Schnorr random relative to y or y Schnorr random. So let's look at for given any y, let's find a real x to real about y, but the low for y Schnorr random, such that the double jump of x compute y jump, and such that every reals below y jump has a relation with every x double jump Schnorr random. Why is it possible? Because if Ry, this Z has a margin 1, that means for sufficiently Schnorr random real, it has a relation with y. But the low for Schnorr y random the double jump of low for Schnorr y random can be arbitrarily high. The Turing degree of low for y Schnorr random can be, the double jump can be arbitrarily high. So it means you can find a low for y Schnorr random x such that double jump is so high, such that every x double jump real has a relation with y. You can find the powerful x double x such x. This is now we know the advantage of for low for Schnorr random because of the double jump we can use, because you can use such forces to build a low for Schnorr perfect set of low for Schnorr random. It can be computed by y double jump, and then that x double jump every pass in the double jump in this pass can be the Turing degree can be arbitrarily high. So it means such x exists. Okay. So because x is low for Schnorr y random, so it means x double jump, sorry, y jump computes x Schnorr random. Because y jump computes y random, so y Schnorr random. So y jump also compute x Schnorr random. Now, because x double jump computes y jump, so let's fix the E. So that phi x double jump equal to y. But every x double jump Schnorr random has a relation with y. So this set A AE range Turing degrees cofinally, because for every y, you can find x Turing above y has this property, Now by TD, then you let's it contains upcomb of Turing degrees. Because you just need to take the Turing closure of this AE, then it's cofiner, then it contains upcomb. Now fix a base for this upcomb, say x0. Now, okay. Now fix such a base, fix x0. So let's look at S omega. Okay, at omega jump. So we can find x0 double jump, x4 jumps, blah, 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 blah. And for any n, you can find let's Rn Turing below phi x0 to the n to the 0, such that this is x 2n minus 2 0 should not random. You can find such a sequence, but because Rn plus 2, R2n plus 2 is is x0 2n should not random. So it has a relation with every real Turing below phi x0 to n. Sorry, it's because it's x0 2n plus 2 random. So it has a relation with every real below phi x0 to n, phi x0 to n for every real. So it means Rn 2n plus 2 has a relation. Then you build such sequence. So we prove that CF plus TD. CF plus T implies WTCR. So yeah, this is an application of TD implies WTCR by recursion theory. And let's look at the other applications. So it's well known why AD is important, because it implies regular properties for sets of reals. For example, CF plus AD plus DC. So every set of reals has a perfect set property. That means every uncountable set of reals has a perfect subset. And every set of reals is measurable and has Bell property. And these proofs are not trivial. They are very tricky. And for different property, you need to use different gains. You need to design very tricky gains to prove this result for different properties. There is no uniform proof. But by sTD, we can actually find a very uniform proof to prove this. And this actually, I guess this also already proved by Wooden. So it's discussed by us. And so let's just look at the proof. CF plus sTD implies a set of reals is measurable. So because we have CCR, because TD implies CCR, and sTD implies TD. So we know sTD implies CCR. So we just need to prove if every measurable subset A is not null, then A must be null. If this is true, then every set of reals is measurable. It's just because given any set of reals A, you take the set B by CCR, let's B subset of A is Borel set, such that the measure of B is the inner measure of A. Then do letter A minus B, then it has a null inner measure. So we just need to prove A minus B is null. So now, suppose every measurable set A, subset of A is null, then we prove A must be null. Now, suppose A is not null. Suppose A is not null, then by the remarks we just said, and so for any x like this R in A, such R is X Shinoda random. So now for any y, we can find x Turing above y, such as x double jump. Sorry, x is low for Shinoda random. And x double jump compute y Shinoda random. Why? Because we in A and also in A Why this is true? Because A is not null, so there must be y Shinoda random real R belongs to A. And the double jump of low for Shinoda random reals can be arbitrarily high. So there must be some x, such x double jump computes y Shinoda random, and also belongs to A. So now this set, it means this set range Turing degrees cofinally by CCR. So now we need sTD. This time we need sTD because we need some structure property. So this set ranges Turing degrees cofinally. Now by sTD, B has a pointed subset. So B has a pointed subset P. Now look at this set C. So this set is sigma 1, 1. It's sigma 1, 1. And of course, this is boldface sigma 1 because it's P, perfect subset. So it's a sigma 1, it's an analytic set. So it must be measurable, but it cannot be null. Why? Because this set has a perfect pointed set, and P is a pointed set. So it means the Turing degree in P ranges Turing degrees cofinally. The reals in P ranges Turing degree cofinally. Then it means, but the phi X double jump computes is X Shinoda random. It's X Shinoda random. So it means this R is Shinoda random. So it cannot be null. If null, it cannot. So if we, as we remarked before, if it's null, then this cannot be true. So this analytic subset is measurable as not null. So we get a contradiction because we assume every measured subset of A is null. So we prove this. So okay, and then by similar argument for Bell property. So you can use low for genericity. Then you get every set of reals has Bell property. And for perfect subset property, you need some more tricky argument. We just skip it. Yeah. But it's a long-standing question whether TD implies the regular property for sets of reals, like perfect subset property. We don't know. And but Sami satisfies, he proved that CF plus TD implies CH. So this is okay. What is CH? It has different meaning. The definition of CH is very tricky without actual choice. It does not mean 2 to the F0 equal to F1. It means it's only either countable or has the same power as reals. So yeah, and what he proved is this version of CH. He proved CF plus TD implies every set of reals is either countable or has the same power as reals, set of reals. Yeah, but we don't know what this is shown. Okay. Okay, we don't know whether CF plus TD implies sTD either. And of course, we don't know whether sTD implies AD either. It's a long-standing question. I can think it's one of the most important problems in such theory, but yeah, we don't know. Okay, let's look at another application for Hausdorff dimension. Okay, let's look at Basikovich and Moran's. No, English should be Davis. Sorry. So it's very old word. Yeah. And I guess Ted already mentioned this result. Yesterday he already mentioned it. For any analytic set, the Hausdorff dimension A can be approximated by its closed subset. So this is a very famous result. And Basikovich, he proved this is true for pi0 series set. And Davis observed actually his argument can be generalized to sigma 1 set, i.e. analytic set. Okay. Recently, Jack Lutz and Neil Lutz, they proved a very important result and built a connection between algorithmic information theory and the fractal geometry theory. So he proved the Hausdorff dimension, given set of reals, the Hausdorff dimension can be classified as this. So this is dimension, effective dimension relative to X for any single real R belongs to A. Look at the effective Hausdorff dimension of R relative to X. Take the maximum R in A, and let's look at the minimum, the most powerful reals, and then the whole Hausdorff dimension equal to this. This is like the major theory in the major theory version. Oh, sorry, Hausdorff dimension version for major theory result, and yeah, it's like like Schnorr, then as I mentioned, it's not. Then it means lex X such that no real. Okay, every real in A is not X random. It's not Schnorr random. And but okay, by using this theorem, Schleiman proved if V equal to L, then but BD's result. Sorry, BD's result theorem fails for light phase pi 1 set. Actually, this set is very simple. It's X in omega 1 X. It's pi 1 set. It has no perfect subset. And yeah, this was proved by Schleiman. Actually, this is also true. This assumption can be weakened to the constructible set of constructible reals is not null. You can prove this result. Yeah. Okay. Now let's look at this result, BD's result further. And okay, let's look at this result. We will use a very recent result proved by Madison School. Low for Hausdorff dimension. So for any real X, there's a real Y, low for actually effective Hausdorff dimension, but the Y jump to above X. So that means low for Hausdorff dimension. The Turing jump for low for effective Hausdorff dimension can be arbitrarily high. It has this mean. So then it's like the Schnorr random in this case, and we can apply this result. So the point is we need the low for some notion such that you have a definable way to make it very powerful. Okay, let's now we prove this result. So assume CF plus TD, then BD theorem holds for every set of reals, for arbitrary set of, not just for analytic. So the means you need, if you want to refute this, you really need some excellent choice. This was also proved by several statisticians, Cron, Fishman, and Jackson from North Texas, and they use very sophisticated argument, and it's a very long paper. You proved by very slightly stronger assumption like CF plus TC plus AD, but we just need CF plus TD. BD theorem holds for set of reals, and the proof actually is very simple. It's very like the measurability. So given a non-empty set A, we just assume for the simplicity, we just assume the Hausdorff dimension of A is 1. Otherwise, it's just same proof. Okay. By the for any y, for any y. Now we know X is less a real X, such that X is Turing above Y. But X is low for effective Hausdorff dimension relative to Y. But X jump can be arbitrarily powerful. So it means phi X jump, like some E, some phi X jump computes effective Hausdorff dimension 1 relative to Y, but also belongs to A. That means phi X jump in A, and also has a Hausdorff dimension relative to Y 1. Okay, Y Hausdorff dimension 1. But the X is low for Hausdorff dimension over Y. So it also has phi X jump also has effective Hausdorff dimension relative to X. So this real set of reals ranges Turing degrees cofinally. Now by sTD, P has a positive subset P. Now the left thing exactly same as the previous proof, like measurability. Now let's see be such set. This is analytic subset of A, and it has Hausdorff dimension 1. Why? Because by Lutz result, this has a Hausdorff dimension 1. Hausdorff dimension 1. Because this P ranges Turing degrees cofinally. So this has a Hausdorff dimension 1. So we find the analytic subset of A has Hausdorff dimension 1. Now we can apply BD theorem. So it means BD theorem holds for every set of reals. So the Hausdorff dimension for arbitrary set A can be postulated by its closed subset. So this is the proof. And actually, it's very powerful. And Cron, Fishman, Jackson, they only proved this for Hausdorff dimension. And it cannot be generalized to other result. At least it's not clear for me how to prove for packing dimension. How to prove this result for packing dimension. But use their result. But our argument can be easily changed, modified to prove this BD theorem also hold for packing dimension. It's because Joyce Price, actually this is a very late result. This result was proved in 1960s, but this result was proved by in 1990s. And for any analytics at A, the packing dimension of A can also be approximated by the closed subset of A. Now, because fortunately, the Madison School's result also hold for packing dimension. This is also true for packing dimension. So we can use a similar argument to prove over CF plus sTD, JP's result also holds for arbitrary set. And also Slammer's result also holds for packing dimension. So it means they fail, assume equal to L. So JP's result fails for pi on one set. But under S plus TD, JP's result for arbitrary set. Now the point is, okay, the problem is there's a huge gap between V equal to L and CF plus STD. And this is a very strong assumption. It's equivalent to the consistent strength of CF plus TC is equivalent to there are infinitely many Wooden cardinals. So this is much stronger than V equal to L. So there's a huge gap. Now the open problem is what is the exact consistent change for BM and the JP theorem for arbitrary set? And we don't know. We don't know whether it has zero, whether it's equivalent to CF consistent or even moving cardinal. We don't know. We don't know. And also there's another question, maybe not related to this, but it's very interesting to us. So what's the consistent chance of one set of Turing degrees is imaginable? By Solovey and Shela and Shela's result, the measurability for sets of reals, the consistent chance of this is equal to the consistency of GFC plus inaccessible cardinal. But Shela's result cannot be, okay, at least some of his students told me Shela's argument cannot be generalized for two set of Turing degrees. So we don't know. It's open. Yeah. Okay. Thanks.
Thank you for a very nice talk. Are there any questions? I have a question. When you are, so you showed us a very short proof using the Turing determinacy of the Hausdorff regularity.
Yeah.
And the conclusion was that you find a analytic non-null set. And
yeah,
I guess the proof of the Hausdorff regularity for analytic subsets, well, I'm not familiar with it, but is it very quick to see that? Or is there a method using this to even show that for the analytic subset that it has the closed?
No, that's different things. At least if you can prove over every Borel subset has this property, then we can prove analytic set. But for Borel set, it's not very easy.
Thank you. Other questions? All right, let's thank Liang again. So we'll have the next talk at